Folks, my name is Kirsten Howard. I'm the Resilience Program Coordinator for the DES Coastal Program. I'm going to pick up where Dave left off and introduce you to the New Hampshire Coastal Flood Risk Summary, Part 2 guidance for using scientific projections by applying it to two of the priority sites identified in the Seacoast Transportation Corridor Vulnerability Assessment. Some of you might be familiar with the Coastal Flood Risk Summary. Part 1 science was published in fall of 2019 and was followed by Part 2 guidance published in March 2020. And the guidance lays out guiding principles and a step-by-step approach to integrate future coastal flood risk information into plans, regulations, and site-specific projects. So for those of you who are gaining some familiarity with the updated DES wetland rules, the guidance informed the requirement for coastal vulnerability assessments to be conducted for projects requiring a wetland permit in the tidal buffer zone. The 9 guiding principles are really equally important, but I'll focus on one in particular today, the second one in this list, which is determining your tolerance for flood risk, because that principle is a little complex and you have to understand it in order to be able to work through the guidance step-by-step process. So your tolerance for flood risk is a subjective concept by nature. It's your willingness to accept a higher or a lower probability of flood impacts for a given project based on a variety of factors that differ depending on that project. So some of the factors highlighted in the guidance include a project's value or replacement cost, its capacity to adapt over time, its importance for public function and safety, or its sensitivity to flooding. So if it floods, maybe that's fine, or maybe that's a really big problem. The 7-step guidance process is depicted here on the slide, starting with step 1, which focuses on defining your project goal, your timeframes, your location, etc. Step 2 is where you select your tolerance for flood risk. I'll call that TFR from now on. Steps 3 through 6 are where you select your coastal flood risk values, from sea level rise to storms to groundwater rise to precipitation. And then you end with step 7, where you do a cumulative risk assessment to conduct. You conduct a cumulative risk assessment and then you evaluate adaptation options. So the steps can be approached in an iterative way. You can see that with the backwards arrows on this figure. You can go back essentially and reevaluate earlier steps as you go. I'll use the Seacoast Transportation Corridor Vulnerability Assessment Site 15 at Cusack Road and then Site 16 at High Street, both in Hampton, from the project that Dave described to walk us through the 7 steps really quickly. It's really important to note that the guidance can be applied at a different scale. So one could theoretically walk through the 7 steps thinking about the Seacoast Transportation Corridor as a whole network, or you can get really site specific or somewhere in between. So for step 1.1, we've defined a fairly simple goal here. And then step 1.2, we've highlighted key features of the site. They're east-west sites, they're east-west connectors. There are 3 culverts, they abut a salt marsh. We've identified in step 1.3 a design life of 2050 and a useful life of 2100. I've kept it simple for purposes of this exercise, but you can choose different timeframes if needed. Based on the 4 characteristics of TFR, I determined that these sites have a low tolerance for flood risk. Someone else doing this exercise might have selected very low, or they might have picked medium, depending on their goals and their knowledge. In step 3, we combine the timeframes from step 1, the TFR from step 2, to determine sea level rise numbers to plan for at these sites. So based on low TFR in 2050, we plan for 2 feet of sea level rise, and in 2100, we plan for 5.3 feet of sea level rise. I'll note that we're using step 3 table A here, which is based on a moderate greenhouse gas emissions scenario. You can use step 3 table B, which is based on a more extreme greenhouse gas emissions scenario and would give you higher sea level rise numbers. For the second part of step 3, we take a look at what these SLR values, sea level rise values, look like at the sites based on available maps, or you could do this with a site survey. So this is the mean high water at the sites in purple today, roughly. And then the image on the left here shows 2 feet of sea level rise at the sites. The image on the right shows 6 feet of sea level rise at the sites, which we're using as a proxy for 5.3 feet, and darker water is deeper water. Both scenarios, when I look at these images, suggest to me some concerning flooding in the future on really a daily basis. You can also look in step 3 at how we expect wetlands to change with higher sea levels. So the image on the left shows current present day wetland conditions. The image on the right shows possible future conditions in 2050 with 2 feet of sea level rise. So you see in the yellow here that salt marsh is expected to migrate northward. Moving on to step 4, we identify and assess how storm risk changes with sea level rise. So looking at current Fema maps, the sites are mostly in an AE flood zone with a base flood elevation of 9 feet nav D88. Hampton and New Hampshire as a whole has a 1-foot freeboard requirement above base flood elevation. With 2 feet of sea level rise on a 1% annual chance storm surge, you obviously see flood depths increase, and even more so with 5.3 feet of sea level rise. Again, darker blue is deeper water, and the actual depths of water can be seen on the sea level rise mapper where I accessed these maps. I'll provide the link to that at the end of the presentation. Following the step 4 calculations, we end up with a 12-foot flood design elevation for 2050 and a 15.3-foot flood design elevation for 2100, which basically gives us the elevations to build structures and facilities at if it's critical that they shouldn't flood in a 1% annual chance storm. So you might be able to justify laying a road at a lower elevation based on its ability to withstand some flooding or to be closed under those storm conditions. And this step also directs you to think about H&H analysis that might be needed for culverts if they need to be built to convey certain water volumes under these same storm conditions. Step 5 helps you understand future groundwater levels that will change with sea level rise. Because groundwater mapping has been done for Hampton, we can look at those maps, screenshots presented here for 2050 and 2100 sea level rise. And then you calculate in 2050 and 2100 the depth to groundwater based on present day depth to groundwater. So I'm going to make a big assumption that depth to groundwater in the present day at these sites is 4 feet. And then we would determine that the 2050 depth to groundwater using some basic math ranges from 3.8 to 1.8 feet at the sites. And the 2100 depth to groundwater ranges from 3.3 to negative 1.2 feet at the sites, meaning that in some locations, groundwater may actually breach the surface of the sites, compounding surface water inundation from sea level rise. Following that, you're directed to consider the implications for your site. In this case, think about culverts, roadbed depth, and what these changed groundwater levels mean for those factors. Step 6 directs you to select precipitation values for your design storms relevant to the project. In the case of a low TFR, you're directed to add more than 15% volume to those present day storm volumes, and then think about what that means for designing at the site. And step 7 ends with some directions for thinking about cumulative future flood risk at the sites, and then considering and evaluating adaptation options that will help you meet your site goals from step 1. Jo Sias is going to walk us through some possible alternatives for these sites. But before I hand it off to her, I'll highlight step 7, table A, which depicts types of adaptation actions that really should be considered in a robust alternatives analysis. They range from taking no action to avoiding flood impacts in the first place, which is most relevant for siting new projects, accommodating the water or living with the water, resisting the water or keeping the water out, and relocating or moving out of the water's way. So I hope this whirlwind tour of the guidance has helped you to think about how to apply it to coastal projects. And here are some links to the guidance and the mapping tool that come in handy if you want to dig deeper. Feel free to reach out to me with any questions or if you'd like technical assistance applying the guidance to a project. Thanks. Thank you. Over to Joe.